Hey guys, it's Bruno, the IB Math teacher. Welcome to week number 7 now of the Ace Your IB Math Exams in 10 Weeks challenge. If you don't know me, I'm Bruno. I used to work at one of the most prestigious IB schools in Brazil as the head of departments, as an HL math teacher, and also I'm an IB math examiner. And for this May 2026 cohort, I've decided to launch this 10-week challenge or 10-week course to better prepare you for the upcoming IB Math, the May exams in IB Math. Each week, we tackle all 5 topics in IB Math, so functions, number and algebra, trig, statistics, and calculus. 1 question per topic. None of the questions is easy. They're all demanding. We mix paper 1 and paper 2 style questions. All of them are IB Math style questions. And this is a way to mimic what you're going to face when you enter your examination room. So you're not going to know exactly what's going to show up in the IB Math exam. So we're tackling all sorts of questions. Do find the PDF in the description of this video so you can download it, print it, and work it out as we go along the video, as we go through the video. And do share these resources with your colleagues as well so you guys can practice together and learn together. So let's get to it. Let's get to week number 7 of the Ace Your IB Math exams in 10 weeks. All right, so let's start with this beauty of an exercise. We have a sector with radius 1, which has infinite circles inside it, and this diagram obviously doesn't show infinite circles but only 4 of them, so 1 2 3 4, and we can see that the radius is decreasing at a certain rate, and we don't know what that rate is, but we will find out. Now the first question is, show that the largest circle has a radius r1 of 1/3. So r1, which is this, it should be 1/3. We're not going to use that, of course. We need to prove it. Therefore, we need to find some sort of way, either using proportions or trig functions, in order to prove this. Now we can see that r1 shows up right here as well. I'm going to color code this, and we can see, for example, another radius r2 over here, which we're going to use later, and so on and so forth. Now all of these, they can be found if you take into account the fact that this radius right here is equal to 1. And also by noticing that these 2 triangles, they're identical, then these 2 angles will be identical as well. Therefore, if this is pi over 3, this would be pi over 6, and this is pi over 6. Meaning, if this is 60, these are going to be 30-degree angles. Now, we need to actually prove that these triangles are congruent. And do notice that this is the RHS case for congruency. We have these triangles, number 1 and number 2, sharing the same hypotenuse, which means that the hypotenuse of triangle number 1 is exactly the same as the hypotenuse of triangle number 2. They are, of course, right triangles, and they also have another side which is identical. Therefore, these triangles are identical. Therefore, if we have a 60-degree angle over here, pi over 3, that means that this is pi over 6, and this is pi over 6 as well. That also means that these angles are 60-degree angles, given that the sum of the 3 angles should be 180. And we can use this right triangle over here to state that the sine of pi over 6 is the opposite side, which is r1 over the hypotenuse. Now we do need to find the hypotenuse, considering that this is r1 as well. The hypotenuse is 1 minus this r1 over here. This is the hypotenuse. So we have 1 minus r1 over here. Therefore, 1/2 is r1 over 1 minus r1. 1 minus r1 is 2r1. Therefore, r1 is 1/3. So this is question A. For question B, we need to find the radius r2, and we're going to use a similar strategy, which means using sine. But now we just need to be a little bit more careful in finding the hypotenuse for that specific triangle. Given that this is r1, this is r1 as well, and this is r2. This new hypotenuse, this orange one, is 1 minus 2 r1 minus r2, which means 1 minus 2 times 1/3 minus r2, there 1/3 minus r2. So we have our sine of 30 degrees, or sine of pi over 6, as the opposite side over the hypotenuse. So 1/2 is equal to R2 over 1 over 3 minus R2. So we have 1 over 3 minus R2 equal to 2 R2. So 3 R2 is 1/3. That means that R3, it is 1 over 9. Now it is given to us that the radii follow a geometric sequence, which means, and by the way, I don't know what this 3 is doing here. This is R2, which means that in order to go from R1 to R2, we multiply a ratio. So the geometric sequence is 1 over 3, 1 over 9, and so on and so forth. In order to find the ratio, we divide two consecutive terms, which in this case means 1 over 9 over 1 over 3, which is 1 over 3. Therefore, if we would like to know what R3 and R4 are, we can just keep multiplying these by 1 over 3. So 1 over 27, 1 over 81, and so on and so forth. So remember that the ratio is 1/3. And the question is, that being the case, find the total area of the infinite series of circles. So right now we're talking areas, not radius. So let's find each individual area. We have area 1 as pi r squared, and the radius here is 1 over 3, so pi over 9. We have this area over here as pi r squared as well, which in this case means pi over 81. And the areas, they do also follow a geometric sequence, given that we're always multiplying by radius squared, which means 1 over 9. To go from one area to the other, we multiply by 1 over 9. Therefore, if you were to build a geometric sequence, not with the radius, but with the areas, we would have pi over 9, pi over 81, pi over 729, and so on and so forth. So the ratio between the areas is 1 over 9. If we're adding all these areas, we should get the first term over 1 minus r, which in this case is 1 over 9. So pi over 9 over 8 over 9, which in this case means pi over 8. Now, if by adding these infinite circles we get pi over 8, and the sector area, which is this whole thing, this whole area, it is equal to half theta r squared. And given that theta is pi over 3, and the radius is 1, we get for the sector area pi over 6. Therefore, the proportion of the sector occupied by the circles is the ratio between pi over 8, which is the sum of these infinite circles, over pi over 6, which is the sector area. That means 6 over 8, which is 3 over 4. Therefore, 75% is occupied by these infinite circles. Now let's jump to the next question. In question number 2, we have a quadratic for which we need to find the inverse. And the way to accomplish that whenever we have quadratics is not to have our quadratic written in general form, but in vertex form. So we need to complete the square or find the vertex using a different method, which is by finding the x value of the vertex as negative b over 2a, and then evaluating the function at that point to find the y coordinates of the vertex. That also works. And that will allow us to sketch this parabola and understand the next steps to be done in this question. So I'm going to use that method actually, which is to find the x value of the vertex, not by completing the square, but by calculating negative b over 2a. I do encourage you to learn how to complete the square, as it is a faster method. But again, any of the two, they work. So let's tackle the exercise. This is our quadratic in standard form. And do notice that it's defined for x less than or equal to negative 2, so only a very specific region of this quadratic is taken into account. Now, f of x can certainly be written in standard form, but it can also be written in vertex form. And in order to find h and k, which are the coordinates of the vertex, we can do the following. H is negative b over 2a. And by the way, what I call a, b, and c, what everybody calls a, b, and c are the coefficients of this quadratic. So a is 1, b is 4, c is negative 10. So in this case, we have negative 4 over 2 times 1, which is negative 2. And k is f of that value, so f of negative 2. So we have, by plugging it into the standard form, negative 2 squared plus 4 times negative 2 minus 10. which is negative 14. Therefore, the vertex is located at negative 2, negative 14, and the vertex form of this quadratic is x minus negative 2, so positive 2 squared, plus minus, which is negative 14. Now, if you were to sketch this curve, you would see something along these lines where the axis of symmetry is at the vertex, which means negative 2. This is the y-coordinates of the vertex, negative 14. And the function is only defined for x less than or equal to negative 2, which means that this is the only valid portion. Now, all this for us to get here and to find the inverse. Now, you might be wondering, do I actually need to do all this? And the answer is not quite. This just makes for a better explanation. For example, graphing the curve, you don't need to do that. Now, let's find the inverse starting with the vertex form, as I mentioned. So we have y equals x plus 2 squared minus 14. We need to switch the variables and then isolate our new y. So y plus 2 squared, which becomes a square root, positive and negative. Therefore, we have our y equal to negative 2 plus and minus the root of x plus 14. Now, which one is the valid one, the positive or the negative one? There's a nice little hack that you can use. Take into account, for example, the point in this curve. So for a portion that this function is actually defined, where x is, for example, negative 3. Now, if you replace negative 3 into your function, you should get negative 13. If the curve, the function, goes through the point negative 3, negative 13, the inverse will go through negative 13, negative 3. And then you ask yourself, for this equation to be true, which sign should I have? Should this be positive or should it be negative? And the answer is it should be negative. So we can get negative 2 minus this 1 that's going to show up over here, root of 1 being equal to 1. So the actual answer is negative 2 minus the root of x plus 14. Now, to wrap this up, we write f negative 1 of x equals negative 2 minus the root of x plus 14. Now, we have the inverse here, which means that we can find also its domain, but we don't have to actually. And why is that? We have the domain of the original one, and we have the range of the original one as well. Y has to be greater than or equal to negative 14. That's exactly what we see in this graph right here. All the y values of this curve are greater than or equal to negative 14. And that means, and now we switch, the domain of this function is x greater than or equal to negative 14, and the range y should be less than or equal to negative 2. And that's one way to find the domain. Now, there's a little trick to do question B, which is actually a common question. The graphs of f and f negative 1 intersect at a given point. Find the coordinates of this point. If you try to take the quadratic and make it equal to the root function, and you're going to try to, for example, square both sides, it's going to be a disaster. Don't do that, okay? A function and its inverse, they're symmetric about the line y equals x, which means this line right here. We have here a better representation of the function f and its inverse. Now, this is the line y equals x. And do notice that whenever they intersect, they also intersect the line y equals x. So instead of doing f of x equals f negative 1 of x, which would be disastrous because it involves an equation which we cannot solve, you can do f of x equals x, which means that if this is the function x squared plus 4x minus 10, and this is the function y equals x, you're finding the intersection by making one equal to the other, which means x squared plus 4x minus 10 equals x. And this is a quadratic that we can solve. We get x1 equals 2 and x2 equals 5, which is the correct one, given that the quadratic is defined for x less than or equal to negative 2. So negative 5 is the only value that fits. And we can see it right here. If you want to find the y-coordinates of this point, then you can just plug it into the line y equals x, given that this point belongs to the line as well. The line crosses that point as well, and then we're done. Alright, so a trig equation to solve in exercise number 3. This is a little bit more involved given that we have to use a few identities, and the best exercises which involve trig equations, they do involve identities as well. This is one that we should do without a calculator, so all the arcs that we're going to find, they're arcs from the unit circle. So let's get to it. Show that cosine of 2x minus sine of 2x plus 1 is equal to this. So you have to decide either to start from the left-hand side and work your way towards the right-hand side, or the other way around. Now in this case, we're going to go from left to right, and by using the following identities, we are going to replace cos of 2x by cos squared of x minus sine squared of x, and sine of 2x by 2 sine of x cosine of x. We still have the plus 1. And it's a good idea to always keep an eye on where you're trying to get, which means the right hand side over here. We're trying to factor out this cosine minus sine, which indicates that there's something that we still need to do. Let's just take a sneak peek to see how this looks like. This looks like the following: 2 cos squared of x minus 2 sine of x cosine of x. Now we do have the negative 2 sine of x cosine of x over here, but we only have one cosine squared, which means that we should convert this into another cosine squared using the following identity. 1 minus sine squared of x equals cosine squared of x, and that's exactly what we have over here. So we do get 2 cos squared of x minus 2 sine x cosine x, which gives us 2 cos of x minus sine of x. So we're done with question A. Now let's jump to B. Hence or otherwise, we need to solve this equation. And we can spot that on the first 3 terms, we have exactly what we got for question A. We can use this to substitute over here, meaning that we can write 2 cos of x, cos x minus sine of x, plus 3 cos of x, now we're talking about these terms right here, minus 3 sine of x equal to 0. And if you put 3 as a common factor over here, we can rewrite this as 3 times cos of x minus sine of x. And we can now factor out this cosine of x minus sine of x. And factoring out pretty much means removing. And what we have left is 2 cosine of x plus 3. All of this equal to 0. Now we have a product which is equal to 0, which means that either the first term or the second term is equal to 0. So let's analyze these two cases. We might have 2 cosine of x plus 3 equal to 0, which means that cosine of x is equal to negative 3 over 2. Now this does not produce any solution, given that there's no such thing as a cosine which is less than negative 1 or greater than positive 1 for that matter. So this produces no solution. However, we have the second one, cosine of x minus sine of x equal to 0, which means that sine of x is equal to cosine of x. We can divide both sides by cosine of x, which gives us a tangent of x equal to 1. Now, from 0 to 2 pi, the arcs that give us a tangent of 1 are pi over 4 and 5 pi over 4. Now there you go, that's it for this exercise. Let's jump to the next one. Alright, so let's jump to this statistics problem, which is by all means not the most sophisticated one, but it's a kind of exercise that shows up every time. And by every time, of course, I don't mean every year, but occasionally it does show up. Now we have a tire manufacturing company that is, in a nutshell, testing whether the tires maintain or hold the air pressure. So they take a tire and just leave it there for a few days and see how the tire pressure reduces with respect to time. Now over here we have time measured in days, and x is used to specify the number of days. And we have tire pressure being modeled by the variable y. So y as a function of x measures the tire pressure as a function of the days that it is stored in this climate-controlled environment. Now, in order to write the regression line of y with respect to x, we need to use our GDCs, which means that we're going to do a linear regression. So the first thing to do is to populate our table with these values. So we're going to edit our table, and I'm going to use L1, which is the first column, to input the number of days. There you go. And then L2 to input the tire pressure. You should do a linear regression where the X list is L1. In this case, right now I'm using a TI-84. L2 is the pressure, and we're going to store, which means clicking on vars function y1, whatever equation that we get, which means a linear one, into our y1. And what we get here is y as a function of x as negative 0.445x plus 38.7 rounded to 3 significant figures. And we can see how strong the association is by checking the value of r. R is negative 0.998, which is a very strong negative linear correlation. Now, what does the gradient and the y-intercept, what do they mean? We have each data point, which is represented over here by these little dots. And this is, by the way, just a rough sketch. And we have our linear regression. Now, the y-intercept means the initial tire pressure, which is y of 0, which in our case, for this linear regression, it is approximately 38.7. This is an approximation of the tire pressure for the instant, or on the instant it was inflated. The tire was inflated. Now the gradient, which is the slope y over x, it is the rate of decrease of the tire pressure per day. Remember that you can find a gradient by doing delta y over delta x, which means the change in y over the change in x. So when the change in x is 1, which means 1 day, what we get for the slope is the change in y, which means the change in the tire pressure. Now this is negative because, well, the slope is negative in this case. It could be a rate of increase for other contexts. We can, with our model, for example, for question D, estimate the tire pressure after 20 days, which in this case is going to be approximately 29.8 psi. And we can do these calculations whenever we're inside the domain that we used to create this model. So for example, in this case, we're going from day 0 to day 24. So anything that we calculate within this range of values, it's fine. If you want to find, for example, the air pressure after 13 days, that will be fine as well. However, anything greater than 24 or less than 0, in this case, of course, less than 0, doesn't make a lot of sense. But after 24 days, the model is not appropriate. Over here we have an extrapolation, therefore it is not. Something that's not appropriate as well is to find the number of days given a pressure. This model is only suited to find the pressure, the air pressure, as a function of days. If you were to find the number of days as a function of pressure, you would need to build a different model using the same data, but when you're doing the linear regression in your calculator, you need to switch the columns. So you need to use x for y and y for x. If you do that, then it's fine. In this case, it is not fine. Now on to question 5, a calculus question. This is one that can be misleading, and there are a few things to be careful with. So let's start with finding the derivative of f of x. We know that p is a constant. Therefore, when you're differentiating p, for example, you get 0. However, if you have a product, or in this case you have p squared over x, which can be rewritten as p squared to the x times x to the negative 1, this constant does stay there, and we differentiate x to the negative 1 using the power rule, so negative 1, x to the negative 2, plus, and now the derivative of x squared, which is 2x. Now f prime of x can be rewritten as negative p squared over x squared, which is x to the negative 2, plus 2x. So question A is done. Now we know that the graph of the function has a local minimum point at 2, 8, which means that at 2, f prime of 2 is equal to 0. If there's a local min at 2, that means that at that point, the tangent, which is represented by the derivative at that point, it is horizontal. So that means that the slope of this tangent, which is f prime of 2, it is equal to 0. But also take into account the fact that 2, 8 is a point that belongs to the function, which means that f of 2, not f prime of 2, but f of 2 is equal to 8. Therefore, using this second equation, we have 8 equals p plus p squared over 2. And right now we're substituting 2 for x and 8 for f of x over here, plus 4. And also, f prime of 2 is equal to 0. Therefore, using this, we have 0 equals negative p squared over 4 plus 4. And we can do this one first. So p squared over 4 equals 4. So p squared equals 16. So p is either positive or negative 4. Let's see what we get for the first equation to see if it's actually positive or negative. So we can subtract 4 from both sides here, and we get p squared over 2 plus p equals 4. Multiplying everything by 2, we have p squared plus 2p equals 8. And we have two solutions here. Either p is positive 2 or negative 4. Now, given that the solution for this needs to also be a solution for the equation above or below, that means that p should be negative 4. This is the only solution for this problem. P is equal to negative 4. And that's it. All right, so that's it for week number 7. We're done with it. We just have 3 more weeks to go. Congrats, by the way, you're almost there. Do share these resources with your colleagues so you guys can study together. And do know, as you know already, everything can be found in the description of this video. Everything is for free. You can just click the links and download the PDFs there and access also the YouTube videos there. Okay, I'll see you on the next one. I'll see you in week number 8.